going to talk about multiplying matrices. Going to talk about multiplying matrices. In fact, we're going to learn how to multiply matrices. Just like in addition and subtraction, you couldn't add or subtract different matrices if their sizes didn't allow it. For addition and subtraction, the sizes just had to be the same. Now, for matrix multiplication, if A is m rows by n columns, and B is r rows by s columns, in order for A times B to be well defined, that is, for you to be able to multiply an m by n matrix by an r by s matrix, these have to be the same. Remember, rows, columns, rows, columns. The columns in the first matrix must be the same as the columns, as the rows of the second matrix. The column of the first matrix must be the same as the rows, number of rows of the second matrix. And this result will be m by s. Okay. In other words, if A is 3 by 5 and B is 5 by 2, you can multiply, so AB, it will be, it says 3 times 5 by a 5 times 2. Since these are the same, A times B is well defined. That is, we can multiply them. Now that we can multiply them, what size will we get? The size will be the outer numbers. It will be a 3 by 2. If it turned out that A was a 3 by 8, A is 3 by 8. You can't multiply A times B. You can't multiply A times B. And the reason that you can't multiply them is they're different size. They're not the appropriate size. They're not allowed to be multiplied. Why? Because the columns in the first matrix, they're not equal to the number of rows in the second matrix. This is not well defined. You cannot multiply these two matrices. So, the number of columns in this matrix must equal to the number of rows in the second matrix. Okay, that's important to know. Now, we're almost ready to multiply matrices, but there's one last thing that I want to talk about, and it's the dot product. Suppose you have 3, 2, 1, that matrix, and you want to dot it with 1, 0, 5. Now, my notation here is a little bit off. I should have a T up there, but let's not worry about that. There's no point in talking about what the T is. It won't help at all. Now, this dot product is called the dot product because there's a dot in between. the dot product is a single number. And basically, this is the first number, the second number, the third number. That's the first number, the second number, the third number. We multiply the first numbers, the second numbers, the third numbers together, and we add up the results. That is, we multiply 3 times 1. We multiply 2 by 0. And we multiply 1 by 5. And these are the 3 products, and we add them up. That is 3 plus 0 plus 5 is 8. That's the dot product. If you have negative 2, 0, 4, and you want to dot it with 3, 1, negative 2, you multiply the first entries, you get negative 6. Plus, you multiply the second entries, you get 0. Plus, you multiply the third entries, you get negative 8. Negative 6 plus 0 is negative 6. Add negative 8, you get negative 14. Okay. You need to be able to do that. It's a dot product. Very important concept for that's going to be used in multiplying matrices. Now, when you actually do the multiplication of matrices, you'll probably never ever say the word dot product, but that's what you're doing. You have 7, 0, negative 2, 4, 1, and you want to dot this with 1, negative 2, 3, negative 4, 5. It's just a few multiplications and addition. You multiply 7 by 1, you get 7. Plus 0 times whatever is going to be 0. Plus negative 2 times 3, negative 6. Plus 4 times negative 4 is negative 16. Plus 1 times 5 is 5. Lots and lots of addition and subtractions and multiplication when it comes to dealing with matrices. 7 plus 0 is 7, plus negative 6. Well, I would love to change both of these to 7 minus 6, which is 1. 1 minus 16 is negative 15. And let's not forget to add the 5. If you owe somebody $15 and you pay them 5, you still owe them 10. So that's a major step in multiplying matrices, knowing the dot product. Okay. So let's multiply two matrices. 2, 3, 1. 1, 2, 4, and this will be 1, 2, negative 3, 0, 1, 4, 2, 1, 5, 0, 0, 1. Now first, let's make sure we can actually multiply these two matrices. This matrix, it has 2 rows by 1, 2, 3 columns. Now, this first entry better be a 3 because these have to match. And look at it. Row 1, row 2, just 3 rows. Perfect. Columns. 1, 2, 3, 4. So it is well defined, and the answer, because these two numbers are the same, so the answer will be a 2 by 4. It will be a 2 by 4. That is, we're going to have 2 rows of numbers and 4 columns. 1, 2, 3, 4. And we are going to dot each row in the first matrix with each column in the second matrix. Like the distributive law. When you have 2x plus 4. You want to multiply this by 3x squared minus 9x plus 1, or plus 11. There are 2 terms in here. And there are 3 terms here. You need to multiply the first term in the first matrix by each term in the second. The second term in the first matrix by each term in the second. But now, instead of saying the words terms, I'm going to say rows and columns. I'm going to multiply the first row by, I'm going to dot the first row with each of the columns. I'm going to take the first row, 2, 3, 1, and I'm going to dot it with the first column. 1, 2, 3. 2 plus 6 plus 3. 11. First row. This was the first row. That's the first column. That's where I put the answer. First row, first column. Now I dot the first row with the second column. 0, 1, 4. 0 plus 3 plus 4. 0 plus 3 plus 4. That's 7. Row 1 by column 2. That's where I put the answer. Row 1, column 2. Now, I'm going to do row 1. I'm going to dot row 1 with columns 3. 2, 1, 5. And I get 4 plus 3 is 7, plus 5 more is 12. Row 1 dotted with column 3. Well, that's just where I put it. Row 1, column 3. Put a 12 here. And then we do row 1. I dotted with column 4. 2, 3, 1. That's row 1. And I dot it with column number 4, which is 0, 0, 1. 0, 0, 1. So I get 0 plus 0, which is 0, plus 1. I get 1. Row 1, column 4, gets 1. Now, there is no, I can't do row 1 with column 5. I can't dot row 1 with column 5. The reason is the second matrix, it doesn't have a column 5. There is no fifth column. So I am done with row 1. Now I go on to row 2. I take row 2, and one by one, I dot it with each of the columns. 1, 2, 3, that's column 1. 1, 2, 4. I will dot it with column 2. 1, 2, 4. I will dot this with columns 3. And lastly, 1, 2, 4. I will dot with column 4. 1 plus 4. 2 times 2 is 4. 1 plus 4 is 5. Plus 12 more is 17. Row 1 by row 2 by column 1. That goes in row 2, column 1. 0 plus 2 is 2 plus 16. 2 plus 16 is 18. Row 2 dotted with column 2. That goes in row 2, column 2 position, right here. Okay, row 2 dotted with columns 3. 2 plus 2 again is 4, plus 5 more is 24, plus 20 more. 4 times 5 is 20. 1 times 2 is 2. 2 times 1 is 2. 2 plus 2 is 4. Plus 20 is 24. Row 2 by column 3. That's where I put the 24. Row 2 by column 4. 1 times 0 is 0. 2 times 0 is 0. 0 plus 0 is 0. Plus 4. 4 times 1 is 4. 0 plus 4 is 4. I put this in row 2, column 4. Row 2, column 4. I put 4. And there's your answer. And like promised, it is a 2 by 4 matrix. Okay. Let's try another matrix multiplication. Now, although the number of columns in the first matrix must equal the number of rows in the second matrix, you don't have to stress on that much. For example, if you have 2, 3, 1, 2, 1, 3, 1, 4, 2, 1, 1, 0. And you want to multiply this with 1, 0, 0, 2, 1, 0, 0, 0, 1. Well, the first thing you should do is take the first row and dot it with each of the columns. If you take the first row and you dot it with the first column, let's write it as a column. So first you multiply the 2 by the 1, the 3 by the 0, the 1 by the, the 1 by the 0, but not that 0, the 1 by the 0, and then there's nothing to multiply the 2 by. And that's exactly how you know this is not well defined. Okay? The number of entries here is not the same as the number of entries there. For example, this problem has 3 rows, so this matrix has 3 rows and 4 columns, this first matrix. This matrix has 3 rows by 3 columns. Since these are not the same, you can't do this problem. And notice that I figured out we couldn't do it without even finding the size of the matrices. But we're going to make this work. We're going to make this work by removing a column in the first matrix. The first matrix is 3 by 3, and the second one, coincidentally, is also 3 by 3, but more importantly, these are the same. So the answer, the matrix we're going to get, will be a 3 by 3 matrix. 3 rows, 3 columns. All right, so I'm going to take the first row in the first matrix, and I'm going to dot it 1 by 1 with each column of the second matrix. This is the first column, and I get 2 plus 3 zeros plus 1 0. I get 2 plus 0 plus 0, which is 2. First row, first column. That's just where I put it. First row, first column. Now I am going to dot the first row with the second column, 2, 1, 0. So I get 4 plus 3 is 7 plus 0. 7 plus 0 is 7. First row, second column. That's where I put the 7. 1, row 2, row 3, column 1, column 2, column 3. Row 1, column 2. Now I am going to dot row 1 with column 3. 0, 0, 1. So you get 0 plus 0 is 0 plus 1. And I put this in row 1, column 3. And then I attempt to multiply or dot the first row with the next column. But there is no next column. So I am now done with row 1. Okay, let's all applaud that we're done with the row 1, because we hate doing this. So it's very tedious, but you need to know how to do this. Now let's do row 2. I'm going to dot row 2 with each column of the second matrix. 1, 0, 0, column 1. Then we're going to take row 2, and we are going to dot it with column 2. 2, 1, 0. Then we are going to take row 2, and we are going to dot it with columns 3, 0, 0, 1. And again, the last time I'm going to mention it, but there should be a T up there. Okay, there should be a T there. But we're getting the same answers whether we write the T or not. All right, 1 times 1 is 1, and the next two entries get multiplied by zeros. So the only thing that survived is the 1. Where does the 1 go? Row 2, column 1. Row 2, column 1. Goes right here. Good old 1. Then we do the dot product for row 2 and column 2. 1 times 2 is 2, plus 3 times 1 is 3, plus 1 times 0 is 0. 2 plus 3 is 5. Add 0. Still get 5. Where do I put 5? Row 2, column 2. 5. Notice, row is 2. The column is also 2. Now I do row 2 with columns 3. First two numbers get multiplied by 0. 0 plus, and the results will be 0. 0 plus 0 is 0, plus 1 times 1 is 1. 0 plus 1 is 1. Row 2, column 3 is right there. I know. So when I look across, there's row 2. When I look up, there it is, column 3. Row 2, column 3. So now I am done with the second row. Again, there's no more columns to dot the second row with. So now we go on to the third row. Now we go on to the third row. We're going to dot the third row, 2, 1, 1, with each of the columns of the second matrix. 1, 0, 0, 2, 1, 0, and lastly, the last column, 0, 0, 1. So rows 3 by columns 3, rows 3 by column 2, and rows 3 by column 1. 2 times 1 is 2, and the rest of the products are zeros. 2 plus 0 plus 0 is 2. 4, 2 times 2 is 4, plus 1 more is 5, plus 0. 5 plus 0 is 5. Put this in row 3, column 2, right there. Put this number in row 3, first column. And we're almost done. 2 times 0 is 0. 1 times 0 is 0. 1 times 1 is 1. 0 plus 0 plus 1. Good old 1. Row 3, column 3. 1. Matrix multiplication. Multiply or dot each row of the left matrix with each row of the right matrix. Next thing I'd like to talk about is, well, what would happen if you multiply 3 matrices together? What if you multiply 3 matrices together? Well, in order to make up one nicely, just make sure it's going to work. Let the first one be 3 by 2. So the second matrix would have to start off with a 2. And let's go with a 2. That means, since these are the same, this product will be 3 by 2. And I want to multiply this product, which is 3 by 2. It doesn't matter how it came to be a 3 by 2. For the record, it came to be a 3 by 2 by multiplying 2 matrices. One 3 by 2, the other one 2 by 2. So this matrix will have to start off with a 2, and let's make it a 3. So in the first bracket, we have the results are 3 by 2, and we're going to multiply by our 2 by 3, and this all makes sense because those are the same, and our answer will be 3 by 3. Okay, so let's do this. The first matrix is 3 by 2. It has 3 rows, 2 columns. There's my 2 columns. Here are my 3 rows. The next matrix is 2 by 2. 2 rows, 2 columns. The next matrix is 2 by 3. 2 rows with 3 columns. 1, 2, 3 columns with just 2 rows. Now, for this level course, I'm not going to prove that matrix multiplication has the associative property, but it does. In fact, you do not have to multiply the first 2 matrices together first. You don't have to multiply these together. You do not. I'm not saying I won't, I'm just saying you don't have to. If you choose to, you can move the brackets. Just like 2 times 4 times 7, 2 students can do this problem correctly. The first one can multiply the 2 and the 4 together first, get 8. 8 times 7, 56. The other student could say, you know what, I don't know what 2 times 4 is, but I know what 4 times 7 is. And believe it or not, the student who doesn't know what 2 times 4 is actually knows what 2 times 28 is. You get the same answer. Now, before we do this problem, something just came up in my mind that I think that we should get out of the way first. Does matrix multiplication have the commutative property? Does it matter if you multiply A times B or B times A? Doesn't matter. Well, you know, if A is a 2 by 3 matrix and B is a 3 times 4 matrix, well, A times B will be well defined. A is 2 by 3 times B, which is 3 times 4. Since these are the same, the answer will be, you will get a 2 by 4 matrix. Say A times B is well defined. Notice that B times A is not. B is 3 by 4, and A is 2 by 3. Not only will A times B not equal B times A, but B times A, since 4 and 2 are not the same, it's not even well defined. That is, you can't even multiply B times A. Okay. But now you may say, well, what if they're both well defined? AB and BA. Well, suppose A is 2 by 3, and matrix B is 3 by 2. Well, what will A times B equal? A is 2 times 3, 2 by 3, by B, which is 3 times 2. Since these are the same, we will get a 2 by 2 matrix. But if you did B times A, I'm doing a lot of theory here. B times A is this 3 by 2. I want to multiply that with A, which is a 2 by 3. Those are the same. 3 by 3 will be the answer. A 2 by 2 matrix will never equal a 3 by 3 matrix. Nor did we really ever define equality. Two matrices are equal if they have the same exact entries. They have to have the same exact entries. Okay. Now, I want to do something that you might like better. Suppose A is 2, 1, 3, 1, and matrix B is 3, 0, 2, 1. Let us compute A times B, which in some books, for the record, just might be AB. That is, what is 2, 1, 3, 1 times 3, 0, 2, 1? Well, when you dot the first row with the first column, you get 8. 2, 1 dotted with 3, 2. You get 6 plus 2, which is 8. When you dot the first row with the second column, you're going to get 1. 2 times 0 is 0. 1 times 1 is 1. 0 plus 1 is 1. Now we're going to do the same thing with the second row. 3, 1. I'm going to dot it with 3, 2. Looks like you get 11. 9 plus 2 is 11. Second row, first column. Now we're going to take the second row and dot it with the second column, and I will put the result in the second row, second column position. 3 times 0 is 0. 1 times 1 is 1. 0 plus 1 is 1. So that is what A times B equals. Take the space. Let me get rid of this. Now I'm going to do B times A. I'm going to get the same size matrix, but they won't be equal to one another. They will not be equal to one another. What is BA? Well, matrix B is 3, 0, 2, 1, and matrix A is 2, 1, 3, 1. So I'll multiply or dot the first row with the first and then the second column. 3, 0, and I dot it with the first row, the first column, the first row with the second column. I get 6 plus 0 is 6. Second row, first column. Sorry, first row, first column. 6. And I can stop right here. That's not a 6. They're not equal. But let's go on. First row with second column. 3 plus 0 is 3. First row, second column, put as 3. Now let's do the second row with each of the columns. Let us do the second row dotted with the first column. We get 4 plus 3 for 7. Second row, first column I put 7 in. Second row, I dotted with the second column. 2 plus 1 is 3. Second row, second column. They're not equal. Matrix multiplication does not commute. However, it has associative property. As long as the sizes are such that the multiplication makes sense, you can multiply in any order that you feel like. Well, you can invoke dissociative law. You can invoke dissociative law. You can move the brackets. In this problem on top, I choose to multiply the first two together. And just like when you have 7 times 2 times, 7 times 3 times 2, you can multiply the first two numbers, and whatever answer you get, you multiply it by the next number. And you get your result. Same thing up here. We're going to multiply the first two matrices, and whatever answer we get, we multiply it with the third. First row, first column. Only the two, let's put it here. 3, 2, dotted with 0, negative 2. You get 0 plus negative 4, negative 4. This is row 1, column 1. Negative 4. Whatever answer we get, we'll multiply it by the next matrix. 1, 2, 3, 0, 1, 0. 1, 2, 3, 0, 1, 0. Now we are going to take the first row and multiply it by the second column. I'm going to take the first row, multiply it by the second column. And when I say multiply, I mean dot. I'm going to take the dot product between the two. 3 times 1 is 3. 2 times 0 is 0. 3 plus 0, 3. Row 1, column 2. That's where I'm going to put it. Now, I'm going to take the first row and attempt to multiply it by not the first column, not the second column, but the third column. And I'm going to say, oh, there is no third column. So I'm going to go on to row number 2. I'm going to take row number 2, and I'm going to dot it with column 1, column 2. Row 2 is 0, 1. Row 2 is 0, 1. I'm going to dot it with column 1, column 2. 0 plus negative 2 is negative 2. 0 plus 0 is 0. So row 2, column 1, I put negative 2. Row 2, column 2, I put 0. Okay, I am now done with row 2. I did row 2 from the first matrix with each of the columns in the second matrix. So now I'm going to go on to row 3. Row 3 is 1, 0. Row 3 is simply 1, 0. Row 3. Row 3, 1, 0. 1, 0. So I get 0 plus 0 is 0. 1 plus 0 is 1. Okay, so the third row, row 3, column 1 is 0. Row 3, column 1 is 0. And row 3, column 2 is 1. Okay. So I multiplied the first two matrices. And our answer is right here. Now I need to multiply that by the third matrix. Let's clean up the bottom and let's do this. We are going to take the first row, negative 4, 3, and we are going to dot it with the first column. We are going to take the first row and dot it with the second column. And we are going to take that first row and we are going to dot it with the third column. And we are going to record our answers. Negative 4 plus 0 is negative 4. First row, column 1, negative 4. First row, column 2, negative 8 plus 3. Negative 8 plus 3, negative 5. Row 1, column 2, the negative 5. Negative 12 plus 0, negative 12. Row 1 was column 3 is negative 12. Now, I do the same thing with, I'm done with row 1. I dotted it with the first column, the second column, the third column. Now I go on to the second row. Negative 2, 0. I am going to dot it with the first row. I am going to take the first column. Take the second row and dot it with the second column. And I'm going to take that second row, dot it with the third column. Row 2, column 1. Row 2, column 2. Row 2, column 3. Negative 2 plus 0 is negative 2. Negative 4 plus 0, negative 4. Negative 4 plus 0 is negative 4. Okay. So the third column is 3, 0. Sorry about that. Got the same answer. I got a little suspicious. Negative 6 plus 0 is negative 6. So row 2 will be negative 2, negative 4, negative 6. Why is that? Column 1, column 2, then column 3. Negative 2, negative 4, negative 6. Look at all of these negative numbers. Okay, now we are going to go on to row number 3. And we're going to dot row number 3 with each column in the second matrix. It's always the rows in the left matrix times the columns in the second matrix. So row 3, dotted with column 1. 0 plus 0, 0. Rows 3 with column 2. 0 plus 1 is 1. So 0, 1. And now row 3, we dot this with columns 3. Get 0 plus 0 is 0. And there is your matrix multiplication of those three matrices. Here is the answer. And what you could do as an exercise is multiply these two first, and then multiply that result by this. Now, I know I'm going to be wrong here, but if you multiply those two matrices, and you get 7, 0, first at least let me get 7 zeros, 3, 2, 1, 0. That's the right matrix. You must put this on the left. You must put this 3, 2, 0, 1, 1, 0 to the left. And assuming by some miracle this is right, when you multiply these two matrices, you will get the answer that we got a couple of minutes ago. The next and last thing I want to talk about here is something I probably should have included a little bit earlier, but that's about equality. If you come to know that 2, 3, x, 0, y, z, negative 1, 2, 3 is equal to 2, 3, 3, 0, 1, 4, negative 1, 2, 3, well, every entry has to match. These have to be the same, and they are. These have to be the same, and they are. These have to be the same. That is, x must be 3. Instructions is to find x, y, and z. Those have to be equal, and they are. These have to be equal, and that means that y must be 1. And these two have to be equal. Z must be 4. The negative 1's match, the 2 matches, and so does the 3. So here is your simple answer. Now, if this were, say, negative 3 or 8, you should just say they're not equal. Because no matter what you let x, y, and z be, 3 and 8, the bottom right entry, row 3, column 3, they have to be the same, but they're not. No matter what x, y, and z are, 3 doesn't equal 8. Okay, but since it was this 3, it is correct that for these two matrices to be equal to one another, that x be 3, y equal 1, z equal 4. When we're solving what's called system of equations, we'll run into these again. This completes the section on multiplication of matrices.